Okay, so as promised in this video, we're going to explore a technique for finding the area underneath the curve of a velocity function. So let's imagine that the graph of the function here in black illustrates our trip to the beach. And we want to know, given this information, how far we traveled from the time we left home until we reached the beach. That means that we'd have to find the area under this curve. Using our geometric shape approach that we used in the last video, we could make the area under this curve into a geometric shape and then find the area of that geometric shape to find how far we traveled. Well, obviously it's not easy to find a geometric shape that will fit underneath this curve. But let's just imagine for a second that we could get a pretty good estimate by creating one single rectangle underneath this curve. And that's the rectangle that you see in red. Finding the area of this rectangle would give us an okay approximation. As we can see, the height of the rectangle is below the curve on the interval from 0 to 3, but then the height of the rectangle is above the curve from 3 to 5. So if we were to find the area underneath the curve from 0 to 3, that would give us an underestimate of the total distance we traveled, but then on the interval from 3 to 5, we would have an overestimate of the distance that we traveled because the rectangle itself is above the graph of the function on the interval from 3 to 5. But is there a better way for us to get a better approximation? Well, what if, rather than using one rectangle to find the area under this curve, what if we increase the number of rectangles to 5? Here you can see we have a rectangle on the interval from 0 to 1, 1 to 2, 2 to 3, 3 to 4, and 4 to 5. That gives us 5 rectangles. This approximation would be better than our first one because we're not overestimating or underestimating as drastically as we were with one rectangle. If we increase the number of rectangles to 10, that would give us an even better approximation because our overestimations and underestimations are even less at this point. What if we increase the number of rectangles to 20? Now our estimation is even better. How about 50 rectangles? Or 100 rectangles? Or 200 rectangles? I think you can see where we're going with this. The more rectangles we use to estimate the area underneath the curve, the better our estimation becomes. So all we would have to do is find the area of each one of these rectangles and add all of those areas together to get the total area under the curve, and that number will be a very, very, very close approximation to the actual area underneath the curve. And this is what's called a Riemann sum. To find a Riemann sum, we just divide the area under our graph into rectangles. We find the area of each of those rectangles and then add those areas together to get the total area under the curve. And the more rectangles we use, the more accurate our estimation becomes. So a question that you should ask at this point is, well, if I divide the area under my curve into 200 rectangles or 300 rectangles or maybe even infinitely many rectangles to get the best approximation that I possibly can for the area under my curve, how in the world do I add up the areas of that many rectangles? Well, that's a question we're going to answer in a future video. But for this video, we're going to focus on dividing our area under our curve into rectangles into a smaller number of rectangles. And then from there, we'll develop an idea and a process and a procedure for finding the area underneath the curve with an infinite number of rectangles. Now, even with adding a finite number of rectangles, there are a few different ways that we can approach this problem to get varying estimates. And that's what we're going to talk about in the next few videos. The different methods of applying a Riemann sum to get varying estimates of the area underneath our curve.